Hi, I'm Jeff Groh, and this is Differential Equations, Lecture 15. Consider differential equations of the form dx dt is some vector-valued function of x. In particular, we're not assuming that these are linear, and we're not assuming that this depends on both the independent and the dependent variable. Instead, equations of this form are said to be autonomous. A differential equation of the form x dot is a function, vector-valued function of x alone, is called autonomous. It's independent of this independent variable t on the right-hand side. If f of x naught is equal to the zero vector, then we say that x naught is an equilibrium point. Of the differential equation x dot equals f of x. You can see that if you plug this point x naught in, then the point can't drift from that point because the derivative is zero. It won't change once it's at that point. And so that's why these are called equilibria of these sorts of differential equations. Bringing this back to our first-order linear systems, these are autonomous, and the equilibria, provided A is invertible, are only x equals 0. We've already seen situations where we have these eigenvectors pointing in different directions in the xy plane. In this case, we have these certain directions on which the solution satisfies certain principles. If lambda 1 and lambda 2 are both real and positive, then along these lines, in the directions of these eigenvectors, solutions will exponentially grow away from the origin. In the other direction too, it'll grow away from the origin. So it depends upon how big the eigenvalues are relative to one another, which one you trend towards. But let's suppose that this one is bigger. In any case, we'll run away from the origin in each case. You can see that in this case, the origin itself is acting like a source. The solutions are drifting out of that, kind of as though you have a hose coming out of a plane and having water drift away from that hose. In this case, we call this a source. We're going to make a definition. If the eigenvalues of A all have positive real parts, as we've seen, some eigenvalues can be complex, but if the real parts are all positive, then for the differential equation x dot equals ax, we classify the equilibrium at the origin as a source. So a source occurs when the real parts of all the eigenvalues of the coefficient matrix A are positive. This leaves open the question, what happens in the case that you have complex eigenvalues? As we've seen, you get oscillation in those cases. We should look at that in more detail. As you'll recall, solutions having complex eigenvalues look like C1 e to the alpha t times u cosine beta t minus w sine beta t plus C2 e to the alpha t u sine beta t plus w cosine beta t. You'll see that solutions of this form, if alpha is positive, will spiral outward like this. We'll make a special definition in this case. A source arising from complex eigenvalues is called a spiral source because they spiral out from the equilibrium at the origin. Similarly, if all the eigenvalues of A have negative real parts, the equilibrium at the origin for this differential equation x dot equals ax is called a sink. In this case, the solutions will exponentially decay in towards the origin from all directions. However, if they arise from complex eigenvalues with negative real parts, then they spiral in towards the origin. And this will be called a spiral sink. So if the eigenvalues are complex with that coefficient of the imaginary unit not zero, we call the origin a spiral sink. There are other possibilities besides sources, sinks, and spiral sinks. What if the real part of a complex eigenvalue is zero? By trichotomy, there are three cases: positive, negative, or zero. So, if the eigenvalues of A are complex, with real part zero, we call these pure imaginary. The origin for the differential equation x dot equals ax is called a center. If you think back on the form of complex solutions in this case, solutions can't exponentially grow or decay away from or towards the origin, and so all they can do is oscillate, and they'll follow little cycles around the origin in these little closed loops. It's easy to give an example of a center. Consider x dot equals 0, negative 1, 1, 0, x. Let's find the eigenvalues. We'll take the determinant of minus lambda, minus 1, 1, minus lambda. Minus lambda times minus lambda is lambda squared. When we subtract going the other way, we'll subtract a negative 1, making this plus 1. Moving the 1 over becomes negative and taking a square root. The eigenvalues are plus or minus I. This gives alpha equal to 0, beta equal to 1. Finding the eigenvectors associated with lambda equals I, you'll remember we have to solve the system a minus lambda I up against 0. So we subtract lambda from the diagonal elements. So we'll have minus I, minus 1, 1, minus I. It may not seem obvious, but if we multiply the second row by I and add to the top, we can get a row of zeros. It doesn't matter which row we cross out because they're dependent on each other. They are just multiples of each other. So this gives us an eigenvector, negative 1i. You can see that this decomposes into real and imaginary parts. It's negative 1, 0 plus I times 0, 1. This will be the vector u. This will be the vector w in our solution. It follows that the solution is then C1. E to the alpha t is going to be 1 since alpha was 0. U, which is negative 1, 0, times cosine beta, beta was 1, t, minus w sine beta t, plus C2, negative 1, 0, sine of t plus 0, 1, cosine of t. If we choose C1 to be negative 1 and C2 to be 0, then the solution takes the form, if this 0, this whole thing goes away. If this is negative 1, we're going to have a positive 1 times a cosine in the first coordinate and a positive times a sine in the second coordinate. So basically we have a parametric function with x equals cosine t and y equals sine t. If x is cosine t and y is sine t, that implies that x squared plus y squared equals 1. Every point on this parametric curve will lie on the unit circle. But there's a little bit more information that we have as well. Notice that when t is equal to 0, cosine of 0 is 1, and sine of 0 is 0, placing us here when t is equal to 0. If t takes a small positive value, maybe something between 0 and pi over 2, something in the first quadrant, we know that both cosine and sine are positive in the first quadrant, which means the curve has to go from this point into a place where both x and y are positive, namely the first quadrant. So this curve is going to go around the circle in a particular direction. It has an orientation. In particular, it will go around the circle in a counterclockwise fashion. We call this solution a center. It goes around the equilibrium point at the center. We've now dealt with all possible cases when we have complex eigenvalues. For real eigenvalues, we've dealt with two cases, where all the eigenvalues are positive or where all the eigenvalues are negative. However, it is possible to have both positive and negative eigenvalues. In this case, you'll have these eigenvectors and these eigendirections. In one direction, with a positive eigenvalue, the curves will tend to go away from the origin. In the other direction, if you have negative eigenvalues, the curves will exponentially decay in towards the origin. And if you perturb off of those, then you go from in towards the origin along that one axis and then out along the other. So you'll end up with curves like this. In this case, the origin is called a saddle point. We make the following definition. If the eigenvalues of A are real, with some positive and some negative, we call the equilibrium at the origin for the differential equation x dot equals ax a saddle point. For example, let's look at x dot equals 2, 1, 0, negative 3x. Since the coefficient matrix is upper triangular, we can see that the eigenvalues are 2 and negative 3 right away. Subtracting 2 from the diagonal elements, we see that the y-coordinate has to be 0 and the x-coordinate can be anything. That gives us eigenvectors that are scalar multiples of 1, 0 for lambda equals 2. For lambda equals negative 3, you subtract negative 3 from the diagonal elements, meaning you add 3. So that's going to be 5, 1, 0, 0, 0, 0. That gives us eigenvectors of the form 1, negative 5. Okay, so along the direction 1, 0, we're going to have exponential growth along that x-axis. The other eigenvector is 1, negative 5, pointing down here. So along that line, solutions are going to exponentially decay in towards the origin. So the solutions off of those two lines will look something like this. We need to make a definition. If all eigenvalues of A have the same sign, we call the origin, or of course the linear system x dot equals ax, a node. If the geometric multiplicity equals the algebraic multiplicity for all eigenvalues, then we call the node proper, or we call the origin a proper node. Otherwise, it is called an improper node. Degenerate nodes are the same thing as improper nodes. You'll sometimes see the word degenerate applied to these. Along the eigenvector direction, you may have either exponential growth or decay, but there is no other eigendirection. And so what you'll see is curves kind of doing something like this, going off in these other directions, like this. It's possible for the 2x2 case to classify these equilibria at the origin by the trace and determinant. Of a 2x2 matrix. If you have a 2x2 matrix A, B, C, D as your matrix A, then the trace of A is just A plus D. The determinant of A, which we are going to denote in this section by the uppercase Greek letter delta, will be AD minus BC. Turns out these two are sufficient to classify the nature of the equilibrium of the origin. To see this, suppose that A is just some general matrix A, B, C, D. We can calculate the eigenvalues by subtracting lambda from the diagonal elements and calculating the determinant. This gives us A minus lambda, D minus lambda minus BC. Foiling this out, you'll have lambda squared. You'll have a minus A lambda and a minus D lambda. Factoring out the negative and the lambda, we'll have A plus D lambda. Then we get plus AD minus the BC that's already there. If you denote the determinant by delta and the trace by t, you can see that what we're getting here is minus the trace times lambda plus the determinant. Since the characteristic equation is, in all cases, in the 2x2 case, lambda squared minus the trace times lambda plus the determinant, we can solve this using the quadratic formula. We get minus the negative trace, or just t, plus or minus the square root, minus the trace squared gives you t squared, minus 4 times 1 times delta, all over 2 times 1. You can see that the nature of these will be determined by the trace and also t squared minus 4 delta. Let's deal with the complex case first. The complex case occurs when t squared minus 4 delta is less than 0. In this case, if t is positive, you get a spiral source. If t is negative, you get a spiral sink. And if t equals 0, you get a center. Notice that there's a dividing line, t squared equals 4 delta, between the complex case and the real case. If we think about that in terms of a trace and determinant axis, this represents a parabola in the trace determinant plane. If we're assuming that t squared minus 4 delta is less than 0, that implies then that 4 delta is greater than t squared. That puts us into the region above the parabola. Above the parabola with t positive, we have spiral sources. If t is negative, we have spiral sinks. And when t is equal to 0, you have centers. So centers lie on the positive delta axis. Notice that if delta is negative, then the thing underneath the square root, the discriminant, will be not only positive but bigger than t after you take the square root. That means since you have a t here and then plus or minus something that's larger in magnitude than t, one eigenvalue will be positive and the other one will be negative. That means everything in the lower half plane where delta is negative is a saddle. Everything down here. That leaves open the region between the t-axis and the parabola. In between, when t is positive, you'll end up with sources where t is positive, and when t is negative, you end up with sinks. Along the parabola itself, you get repeated eigenvalues, which may be some kind of node, whether it's degenerate or not, will depend upon the particular matrix. As some quick examples, suppose we have x dot equal to 2, 2, 1, 3x. You can see the trace is 5, and the determinant is 6 minus 2, which is 4. Now, the trace is positive. The determinant is also positive. T squared minus 4 delta will be 25 minus 16, which is 9. Since this is a positive number, that means our eigenvalues are going to be 5 plus or minus the square root of this, 3, divided by 2. You can see that they're both going to be positive. We're going to be in this region over here, giving us a source. As another example, let's look at x dot equals 2, 6, 2, negative 2x. The trace is equal to 0, whereas the determinant is equal to negative 4 minus 12. On the plane, t equals 0 puts us on the vertical axis, and since delta is negative, we have a saddle. If x dot is 0, 2, negative 3, 2x, then the trace is 2, and the determinant is 0 minus negative 6 gives you a positive 6. You can see that here we're in the upper half space because delta is positive, but t is equal to 2. Let's look at t squared minus 4 delta. That's going to be 4 minus 24 or negative 20. That puts us above the parabola in the region where t is positive up here. That's going to give us a spiral source. Definitely a spiral because we get a negative under the square root in the quadratic formula, so we get complex eigenvalues. One more example. Negative 3, 10, negative 1, 3. The trace here is 0. So that puts us on the vertical axis. We're either a saddle or we're a center. The determinant is negative 9 minus negative 10, giving us a value of 1. That puts us right here on the t delta plane, and that implies that we have a center.